All right, welcome back to day 7 of our investigation of gravity. Today I want us to think about how does the moon and how do satellites continue to orbit around the Earth and not get pulled to the Earth's surface? Why do they not crash into the Earth? We know that gravity from Earth stretches out into space, holds the moon, holds satellites there, but why doesn't it pull them in? And that's what we're going to find out by today's simulation. We have a simulation called projectile motion, and just like yesterday, it's a game, but it's a game that we can learn things about gravity while we play it. So let's click on projectile motion simulation. It takes us to the PhET site. Click the play button. And then over here, we're going to select the intro. You can play with the rest of these later, but the questions today come from the introduction option. When you start, let's find out all the different things we can adjust here. When you start, notice that you start at 10 meters, and that's where we want to be. I want to show you that you can raise this and lower it. I'm lowering it now. You can raise it higher than 10 meters. Okay, but I'm going to go back to 10, so that's where we're going to use it. And it starts at 0 degrees, the launch here. So you could also start at 45 degrees or 90 degrees and try out all those different things, even lower. Okay. Oh, look at that. And you can, I'm going to take it back to 0 there, because that's what we're going to use in our demonstration today. Also, we can move the target. It starts at 15 meters. We can move it farther away. We can move it closer. Okay, right there, we put it right underneath our statue. Okay, I'm going to put it though back to 15. You're welcome to, as you're trying all of this out, you're welcome to play with these in different ways. Also, I want to bring it to your attention that up here you can turn on air resistance like you would have on during a regular day here on Earth. Today we're going to turn that off though. We're going to pretend like there's no air. No air to slow down these objects when they're falling. Just like we would on the moon, would have no air resistance, okay? Also over here, pumpkin is what's going to be launched out. You can change it to cannonball, tank shell, golf ball, baseball, football, pumpkin, human, piano, car. So any of those things, you can switch it back. I'm going to leave it at pumpkin for now. And then going over here, I want to also show you another important thing. We can change the speed. The initial speed of the launch could be at 15 meters per second. That's where it starts at. It can go all the way up to 30 meters per second, or down to 0 meters per second. So let's start with 10. And the way you fire, fire your cannon is by hitting this red button here. So I'm going to fire. Looky there. I got it right away. First time. It's like I've never, beginner's luck, right? Well, actually, I've done this before. So 10 meters per second gets you right there on the target. If you tried less than that, let's see what happens if I go 5 meters per second. I can hit the red button again. Oh, then I hit the statue. If I went to 15 meters, increased it to 15 meters per second, what's going to happen? I fire my pumpkin, and it goes farther away. Okay, and then let's put it all the way to 30 meters per second. Fire there. Now I'm off the screen. It lands somewhere way over there. I want to just show you a couple of things that I think are important and interesting. Notice that, first of all, whenever you reduce the speed, it fell closer to the cannon. And when you increase the speed of the launch, it ended up farther away from the cannon. Does this mean that gravity changes by your speed? Well, actually it does not. Gravity treats everything the same. You're going to hear me say that a lot. Right here, I want to show you. At this spot, this is after 1 second. 1 second after the launch, okay? The pumpkin was at 5.1 meters off the ground. So from 1 second, it fell to 5.1 meters. That's when we had the slowest speed. when we had the fastest speed, I'm going to go over here again. Over here is 1 second. Gravity was pulling on this pumpkin, okay, for 1 second, and notice where it's at, 5.1 meters. So notice our slowest, our fastest, even the ones in the middle. At 1 second, gravity pulled it to 5.1 meters. 5.1 meters over here. It doesn't matter. Gravity's always pulling it the same. Okay, so it'll be 5.1 meters even if we throw it farther out after 1 second. Now, if we change that, let's change this up here. I'm going to move this back up. And I'm going to change it. Let's get something really heavy. I'm going to get a piano. Alright, so I'm going to launch this piano now. I'm going to launch it at 15 meters per second. Here we go. No, I'm going to change it to 10 because that's what hit the bullseye before, right? So I'm going to launch it at 10 meters per second. That's our velocity for the piano. Ready? 3, 2, 1, fire. Hey, look at that. Even though the piano's heavier, it didn't have any effect or change on its distance, did it? I wonder, did gravity pull it down faster or slower? Let's find out. So I'm going back here. At 1 second of falling, gravity pulling on it down for 1 second. Notice it also was at 5.1 meters. What does that tell us? Gravity pulls everything the same. It doesn't matter if it's a feather, if it's a piano, a pumpkin, a car, gravity pulls everything the same. And if you take away air, you can see that very easily. Okay, there's nothing to push up on it. Air pushes up on things, like it pushes up on an airplane to keep an airplane flying, right? And so air does push up on things. If you have a feather or something lighter, it can create air resistance that make it fall slower. But gravity is always pulling down the exact same on everything. Okay. Now, I'm going to put this back up here. So we talked about how everything is, gravity acts on everything the same. I'm going to reset this. Now, we're going to move the target. I'm going to move it to 25 meters. So farther away, 10 meters farther away. What do I need to do to hit the target with the pumpkin? Well, let's find out. It was 10 meters before. We know that's not going to work. I'm going to start there. So I launched 10. Okay, so I know before that when I slowed it down, it didn't go as far. So let's speed her up. Let's see, let's go to 20 meters per second. Okay, now increasing the speed to 20 meters per second. 3, 2, 1, fire. Oh, that was too far. So let's see, maybe 18? Let's see if 18 hits it. Yes. I wonder if 17 will hit it too. Yes, there we go. Okay, so 17 and 18 both hit the target. 17 meters per second. Would that apply also with a heavy car? If there's no air? Oh, yep. Same thing. Same trajectory. Same height. Gravity is pulling on it exactly the same the whole time. Now, this brings up an important thing about gravity that we haven't talked about yet. Notice how every time we stretch this target, I'm going to pull it as far as I can. I'm pulling it over here past 30 meters. Every time we want to hit something farther away, we have to increase the speed, don't we? Okay, so it's still falling at the same rate, but it's going farther as it's falling, okay, because it has more velocity. So I'm going to now increase this to maximum velocity for this cannon. I fired away. Oh, that went way past my target. So I'll need to slow it down in order to be able to hit that. But this brings up a good question. Imagine if we could speed up this cannon, could go launch something so fast that it goes farther and farther and farther around the Earth. Because the Earth is round, could it fire something so fast that it goes all the way around before it hits the ground? And the answer is yes, that's possible. And in fact, that's called an orbital speed. When you go all the way around the Earth, because you're traveling so fast, gravity's still pulling on you, but you're traveling so fast you're not falling to the Earth, instead you're falling around the Earth. And that's orbital speed. And that's how fast, the orbital speed is what satellites, that man-made satellites have to do, like the Hubble telescope or the International Space Station. They have to have an orbital speed. The moon is a satellite. It's a natural satellite, and it has to be traveling fast enough to stay to go all the way around the Earth. Otherwise, if it slows down, it will crash into the Earth. Same thing's true with the satellites. We've had satellites that are man-made that go too slow, and they end up crashing into the Earth. So as long as they're traveling at an orbital speed fast enough that they fall around the Earth instead of to the Earth, they'll stay in orbit. That orbital speed for the International Space Station is over, let's see if I think it's over 17,000 miles per hour. 17,000 miles per hour. It's close to 5 miles every second. It's amazing. All right, so we've learned a lot here about how satellites and the moon stay in orbit without crashing into the Earth. They have to move very, very fast, in other words. All right, talk to you guys tomorrow. Oh, almost forgot. Before you're done, before you leave this, make sure you go back to the slideshow presentation, click on the projectile form, and I walk you through just the same things that we did just now. And I also have a short video there to show you and to answer those questions. In fact, a lot of these I answered for you, so you can probably go there and answer a lot of those now. All right, talk to you guys tomorrow, and thanks for listening. Bye-bye.